When people think of the disaster at the Fukushima Daiichi nuclear plant, they usually picture a giant wave slamming into a facility and immediately destroying it. That perspective skips over the complex reality of the accident. The sequence really begins on March 11, 2011, when a magnitude 9.0 earthquake strikes just off the northeastern coast of Japan. Look at the scale of destruction in this image. Thousands were killed as the earthquake and initial flooding flattened whole cities, long before any alarm sounded at the nuclear plant. At Fukushima Daiichi itself, the initial safety systems worked exactly as designed. The moment the tremors hit, sensors triggered an automatic shutdown in Units 1, 2, and 3, successfully halting the nuclear chain reactions. If the reactors did exactly what they were supposed to do and stopped the active fission, how did this event escalate into a Level 7 major accident that forced 100,000 people from their homes? As it turns out, surviving the initial shock of a disaster is very different from surviving the hours that follow. Highly complex systems can harbor threats that only reveal themselves after the dust settles. The danger inside a nuclear plant doesn't disappear the second you press the off switch. Stopping the active chain reaction is only the first step in stabilizing the facility. This diagram shows a reactor core after shutdown. With control rods fully inserted, radioactive materials inside the fuel rods still produce intense residual heat. Because of this, the core requires a constant flow of cooling water to pull the temperature away and prevent melting. The earthquake had destroyed the plant's connection to the external power grid. Right on cue, the facility's emergency backup diesel generators kicked in, pumping the water needed to keep those cores stable. At this exact moment, the plant's engineered defenses were working. This facility had successfully survived one of the strongest earthquakes in recorded history. Then the ocean retreated, and the real catalyst arrived. Tsunami waves, some exceeding 10 meters in height, crashed into the coastline, with enough volume and force to breach the plant's existing seawalls. When that water flooded the lower levels, it submerged the critical electrical equipment and seawater pumps. In this diagram, you can see the result. Flooding kills the backup generators. The circulating water suddenly stops, systems go dark, and without cooling, the fuel rods glow white hot. Inside the units, extreme temperatures cause the cores to warp and melt. The Fukushima meltdown resulted from a specific sequence of flooding that systematically starved the facility of the electrical power needed to sustain its cooling cycles. Between March 12th and 15th, a series of massive explosions tore through the facility. It is important to clarify that these were not nuclear detonations. The extreme heat from the melting fuel chemically reacted with water to create a buildup of highly flammable hydrogen gas, which gathered near the top of the reactor buildings. Eventually, the trapped hydrogen ignited. The blasts blew the concrete roofs off the buildings, exposing their internal structures and releasing radioactive material into the atmosphere. With radiation now escaping, authorities were forced to rapidly expand the evacuation zone around the plant. Over 100,000 citizens had to leave their homes and livelihoods behind. This image of a child being scanned for radiation exposure captures the human stakes of a technological failure. When a sealed technological system is breached, the fallout is never contained to the machinery. It instantly becomes a sprawling humanitarian crisis. Today, the facility is a massive, decades-long project of decommissioning. This field of storage tanks represents the ongoing effort to manage millions of gallons of contaminated water used to stabilize the site. This event prompted the IAEA and regulatory bodies worldwide to overhaul safety protocols, focusing on flood protection and the hardening of backup power against extreme geographical threats. This chart illustrates the core engineering problem Fukushima poses. The flat line represents the maximum expected threshold of a natural disaster. We have to design for the moments when a real-world event violently pierces that threshold and shoots off the graph. We can no longer assume that an isolated safety layer will be enough to save a complex system when things go wrong. As technology advances, our survival relies on our ability to engineer systems that can absorb a fractured link without letting the entire chain whip apart.